Okay, let's get started. So it's great that today we have Zheng speaking in our seminar. Yang has done a lot of work the interface of convex optimization and control. He has received lots of awards for his work, in particular in his career, and most recently the 2025 Donald Exman Award from the American Automatic Control Council. And so we were very lucky to have him here.
Okay, great. Thanks, Dima, for the introduction. So good morning, everyone. Welcome to my presentation today. Today, I'm very happy to be here and to share some recent results on extended convex lifting for parts of magnetic control. And first, I would like to thank my wonderful collaborators for their contribution to this line of work. Rich Pai, Yutu Watanabe, Hong Liao are my PhD student at UC San Diego, and Professor Vijay Tang from Peking University, Professor Nani at Harvard are my long-time collaborators. I would also like to thank NSF for their financial support. So today I'm going to talk about some topic in control. I'm not sure how many of you have taken control classes before, so I would like to begin with a very quick introduction on control theory 101. So in short, control theory is the study of dynamic systems with input. So typically we have this dynamic system with some input, some output. Here we use X to represent system state, U to represent control input, and Y to represent system output. Normally the output could be the state itself or could be a function of the state. And this is a very typical optimal control problem where we try to minimize the cost function of the system state and the input trajectory subject to the system dynamics by choosing appropriate control input sequence. So in principle, you can also consider control as optimization constrained by dynamics over time. Let's look at a very simple example of control where you try to fly a drone from one position to another position. And for this task, the first thing in control is that we typically try to build a model which connects the input to the output. And in this case, for simplicity, let's use a Newton law to build a very simple model for this example. Here we have a position, we have velocity, and we have a Newton's second law that connects the external force to acceleration. And with this model, we can choose the state to be the position and velocity of the drone. And then we can formulate this optimal control problem. We minimize this quadratic cost, and we have this constraint by the dynamic by choosing a property control input sequence. And for this particular simple example, if we use this dynamic, and we see we have very good control performance by solving this optimization problem. And you will see the position is very well regulated with some appropriate control input. Right? So this is a very simple example. And as you can imagine, there's many control applications around our daily life, ranging from the temperature control in this particular semi room to robotic to drone formation. And you can also find many control examples in our daily life, in transportation, in power system, and the smart grid. So in short, control theory, for many of these kind of examples, offers the principled use of feedback loops and algorithms to drive a dynamic system to its desired goal. You have some goal, and based on measurement, you design feedback loop to drive the behavior to some desired performance. So let's now look at a standard block diagram for feedback control. Here we have two blocks. One is your dynamic system. Another block is the feedback policy you try to design. So here we, based on the measurement of the system, we try to design feedback policy to regulate the input such that we may have some good performance, even though we may have some unknown disturbance or uncertainty in your system. And control theory has been very well developed, has a very long history. And if you look at the textbook, traditional methods are often model-based. For example, in the drone flying case, we need to know the model. And then we have very good theory for model-based control, such as LQR, linear quadratic regulator, LQG, linear quadratic Gaussian control, and robust control. And there are many tools for you to use if you have a model. For example, Riccati equation, linear matrix inequality, or dynamic programming. And today I'm going to talk about another perspective in control. We want to do policy optimization. So we choose a policy class for your feedback controller, and we do a policy parameterization using a parameter K. And now the problem often can be formed into this abstract pulse optimization problem, where we try to minimize a control performance, which is a function of your pulse parameter, subject to policy belong to some class. So this is very abstract. And now, with this problem, we may use direct policy update. We refine each policy based on local information gradually to find some good performance. And this kind of procedure probably have seen many, many times in deep learning, where we try to train a neural network to do some classification that's static. Here, we can also use this simple logic to train your controller, where you have a dynamic system in the loop. And this idea actually become very popular in both academia and in practice in the past decades or so, and even more than 1 decade. So we have seen very successful stories from game playing, robotics, and drone flying. So typically what do? We choose a control strategy like KT, and then we apply this strategy to the system. We observe some data, and based on data, you can estimate the negative gradient of the current performance index. And we just refine control strategy and then continue this loop. So this is a very relatively simple idea and also easy to implement in your simulation. And it's also scalable to high dimension problem because you only identify the gradient. You don't need to do any model identification. And it enables model research, maybe with some images, with rich observations. So as you can imagine, there will be some challenges for this pipeline. The first challenge in people talk very often is that the problem becomes non-convex. If you do this pulse optimization, you will get a non-convex optimization problems. And in general, for non-convex optimization, it's usually very hard to get the principal algorithm to achieve optimality, to avoid set point, to escape from local minimizer. And in control, it can also be hard to get theoretical guarantees in terms of robustness, stability, or to have some efficiency to guarantee you have a good control performance. So with this background, in this talk, I'll give you some good news. So the first message I want you to remember is that the non-convex landscape in many benchmark control problems are benign. It's non-convex, but it's benign. So informally, we can show that any station point is global optimal. So this is a very general statement. And this part, I'm going to review some existing results and some results in my own group as well. I'm going to show you that for many classic control problems, it has benign non-convex geometry. If you find a station point, you almost find the global minimizer. And in the second part, I'm going to introduce a framework called extended Convex Lifting to show why we have this property. So it will be a general framework that bridges non-convex cross optimization with convex reformulation. And the details will be in this paper. All right, so with this, any quick questions so far? Feel free to ask questions. If not, I'm going to talk about the first part. Good. Great. So if you have a question, feel free to ask. Let's talk about the first part. So like I mentioned earlier, we know pulse optimization in control is generally non-convex. Let's see why we see this non-convex issue coming from pulse optimization control. So consider this very simple, not simple, standard linear quadratic regulator problem. We have a quadratic cost in terms of state and input. We have a linear dynamics where the state in the next time step is a linear combination of the state at current time and your input at current time. And we want to design a linear static policy. So input will be a linear function of your state measurement. So now the parameter we want to design just a matrix K. Is it a gain? So just a matrix here. And now from a very simple observation, if you do very simple calculation, you plug in this guy into your dynamic, you will see this recursive update. X1 will be A plus BK times X0, and X2, same thing, now becomes square times X0. And continue to you see xt at time t will be a power of a plus bk time your initial state. And now this guy gives you a nonlinear dependency on k. And now if you plug in this xt to the cost, ut to the cost, you will get a non-convex function in terms of k for your cost. So typically, if you write down this problem, you will see some geometry like this. This is a very typical geometry for the landscape in LQR control. You have a non-convex cost function. And if you look carefully, look at the constraint. Already, if you want to do a stabilization, this is a non-convex constraint already. So for control, normally the first thing you want to stabilize the system. You do not want the behavior to diverge. And this constraint is already non-convex into your policy parameters. So formally, we say policy K stabilize the system if the system trajectory converges to the origin or your equilibrium point. So mathematically, this just goes to 0. And now in discrete time, this requires the spectral radius of the closed matrix A plus BK less than 1. And this spectral radius constraint is non-convex, is clear non-convex. Let's give you a very simple example. We have this matrix A to be 0, B to be identity. This means your next state will be your current input. And you can write down this constraint. And it's very simple to confirm this stabilized system, as well, because eigenvalue is 0.5. And now you take a convex combination of the policy parameter, you get this one, and this will not stabilize the system because the eigenvalue will have a magnitude bigger than 1. So this is the picture you should have in your mind. We have a policy space, and if you choose two stabilizing policy and take a convex combination, it often goes outside the stabilized region. So for the constraint itself is a non-convex constraint. And if you go to some other control problem, the non-convexity could be written in other form. For example, if you look at the dynamic output feedback stabilizing policy, this set is not only non-convex, but also could be disconnected. And we have one example here. You have a non-convex connected set, and another example here, you have a non-convex and disconnected region for the set of stabilizing policies. I'm going to talk about this. So it's just saying, so here, in this case, it's just a linear static feedback. It's just your function is a linear function of your x. And in general, if you only have observation y, you may not want to use a linear static policy on y directly. You want to build another dynamic system using your y and generate an input. And that will be dynamic policy. I'll give you a definition soon. And in that case, you may even see like a disconnected stabilizing region. We know like the policy organizing control is non-convex, cost function, constraint are both non-convex. But now I want to give you a very general message here. Policy organizing linear control, I'm going to restrict to linear control, is generally non-convex, but benign. I'm going to show you some benign non-convex property very soon. And this statement applies to many benchmark control problems, including LQR, LQG, robust control, and infinity control. So I'm going to show the property some. So let's look at the LQR problem in particular. We have this block diagram, and in LQR, the dynamic will be a linear dynamic. And here I look at the continuous time, and they also result in discrete time. And the controller is the same thing. We design a linear feedback controller. The U will be a linear function of x, and K will be the parameter you want to design. And so this will be a constraint. You want to make sure the system should be stable to begin with. It means the eigenvalue of the matrix have negative real part. And we want to minimize this quadratic cost of your state trajectory and input trajectory. So this is the basic setup of LQR regulator. It's very standard problem in control theory and very fundamental problem in control theory as well. Now we look at the constraint. The constraint is non-convex, but we can show that the set of stabilized gain is always path connected. So if you have one stabilizing policy, another stabilizing policy, even though you cannot use a straight line connected, but you can always find a smooth path connecting two stabilizing policies. So it means if you start from one policy, it's possible there's another path that leads to another minimizer. So it's connected. And for this result, I want to give you a quick proof because this proof idea will be used very often in the second part of the talk. And we're going to prove this result by convexification. Yes.
So in the standard control problems like LQR and others you mentioned, there the regions can stabilizing these regions cannot be disconnected, right? So
in the static feedback. Okay.
The static.
Yeah, static feedback.
But is there like examples where they're disconnected, but it's very taking some standard example?
So I'm going to show you here. This example is disconnected.
Right.
So this we go to dynamic output feedback policies.
I see.
So in this case,
So when your policy is being up, it's not static.
Not static in this case. But if you only have like output measurement, the set could also be disconnected. And here, what I show is that for a safety bet, so just state, if you have a y that equals c times x, and you have c here, and then you could get the disconnectivity. And I'll show you here why. I'll show you here in this slide why. So this proof it will give you maybe one reason why we have this case, and why if you only have an output, and then you may not have a connectivity. So I'm going to show you a convexification procedure by non-interchangeable variables. So this is our origin set. We want to make sure the K such that this matrix is stable. The eigenvalue of negative real part. And in control theory, there's a very standard result, which says this constraint is the same as you can find a positive definite matrix P such that the matrix inequality is negative definite. This really comes from the Young theory. Okay? And now you look at this constraint, you have a positive parameter K and you have a Lyapunov variable P. It's coupled, it's bilinear, non-linear. And now a very simple idea or very standard idea in control theory is to do change of variable. You say, I define this to be a new variable L. And now this constraint becomes a linear matrix inequality in terms of a new variable P and L. So in this set, it's convex, but you have this coupling. So you can do a change variable. You say, this is my convex set, and for any stabilized controller, I can build it from the element here by using this smooth method. It's just a matrix times inverse of another positive that matrix. It's a smooth method. So we know any convex set is path connected. So we have a continuous image to represent this set. And of course, it should be connected. It's path connected. So the reason is really because we have a convexification procedure for this set, and it's path connected. And now if you go back to the case, if you have a matrix C here, and this change variable may not work. So you cannot prove this connectivity result using this procedure. And really, we can show this connectivity using examples if you have a output measurement only. Right? Cool. Okay, good. All right, so that's the first result. This is path connected. It looks better than general non-convexity. And also the LPR cost. Yeah.
So it's from the first line, though, basically the set of stabilizing controls is the projection convex set.
You mean this one?
Yeah, this is defining a projection.
Yeah, this is defined projection, but it's not a convex set because the variable P exists, it's not given. So you need to, this is also a variable. So it's really saying that the set of
I see.
Yeah.
I see. So in jointing the PK is not.
Yeah. Right. PK is not convex.
I see. That's why I didn't.
Yeah.
Switch to L and then.
Right. So it now become a not a projection. It's kind of a non-linear map.
Yeah, that's an image, and
Yeah.
it's an image of a projection on the non.
Right. Yeah. And this non-linear map actually is very smooth. It's very well defined because P is always polyident. So it's very well defined. So you will see a connectivity for this non-convex set. Okay. And actually, I'm going to use this idea to prove many other results as well in the second part. And the second fact is that the LPR cost is real analytical, and you can take as many derivatives as you like. And in particular, you can write down the LPR cost as a rational function of the path parameter K. So this is the original definition, and by the Lyapunov theory, you can write down the cost in terms of a new variable x, and x comes from a Lyapunov equation. And this is just a linear equation with fixed K. So x will be a rational function of K. You just solve this. X will be a rational function of K, and plug in, so overall, the cost will be a rational function of your path parameter K. So you can take as many derivatives you like. And the third fact is that we can prove if we find a station point for this cost function, it will be the global optimal point. Even non-convex, we can prove this. And actually, the proof is also go to the convex reformulation. I'm going to talk in the next part. So this is general picture you may have in your mind. Not convex, but this is station point, and this will be the only global minimizer. Not only this will be one of the global minimizers. So if you get local stationary information, you will have global optimality. And furthermore, LQR cost even satisfy a stronger condition, which is known as green dominance condition or Poilievre-Loisevic inequality in some literature. So in this case, we can prove that the cost value gap is upper bounded by the norm of the gradient. Okay, from the gradient information, you can not only get whether you are at the global optimal point, you can also get the suboptimal gap. This will be upper bound. And so LQR almost behave like a strongly convex problems under very mild assumption. And then if you have this property is now well known in the optimization, you can use gradient descent, which give you linear convergence. And for these papers, they basically prove this result and then apply gradient descent, and you really get this linear convergence to the global optimality. Right. So this is for LQR, and then we can talk about another example where we do not assume Gaussian noise. In LQR, the noise is assumed to be Gaussian. And here we assume the noise could be adversarial. So we consider the worst case performance. So basically we want to minimize this performance measure. So we consider the worst case of this quadratic cost when you have bounded disturbances. And this really go to the robust control. And similarly, you can put the problem into this form. You can put this problem in this form. And due to the nature of a min-max structure, this is maximization, want to do minimization, and the cost will be non-convex and also non-smooth. So in this case, it will be non-smooth. But we can prove that the cost function is always locally weakly convex. It's not an arbitrary non-smooth non-convex function. There's some geometry here. And we can also prove any sublevel set is path connected and any stationary point is global optimum. Even for this problem, we can also prove this fact. So you may want to use subgradient method to find a global minimizer, even though the problem is non-convex. So we have a simple simulation here. Just do this, and these L will really find the global minimizer for this H robust control problem. So here. It's process noise. The process noise. So we assume it's adversarial. We can choose any bounded energy signature, and you want to minimize this worst case performance. And this is also a standard problem in control theory. And here I want to say, if you look at the problem in terms of cost optimization, you can define the cost function here, and there are some good properties. And in particular, we can prove any station point to be global optimal in this non-convex, non-smooth problem. And we also show subgradient method could do well in this setting. Actually, we are using one result from your past work to show this subgradient method can find a good minimizer. All right. So now we look at the state feedback. Now let's look at the output feedback. So in this case, we do not have a measurement x. We have measurement y. Y will be a linear function x plus some measurement noise. So here you have some measurement noise, and you can not measure state directly. And this is known as linear Gaussian control. In this case, we assume process noise, measurement noise to be a Gaussian IID. And we want to minimize the same performance index. And this is also a very well-studied problem in control theory. And we have a very famous separation principle because we do not have the measurement of state. So the optimal solution will be a combination of common filter to estimate the state with LQR feedback gain based on the state estimation. So this L will be common gain to measure the state, because say can be viewed as a state estimation. And then based on state estimation, you do this LQR feedback gain. So this will be a dynamic system because from Y to U, you have another differential equation going on. That's a dynamic system. So in this case, we need to consider a larger class of policy, not just a linear static policy. We consider the class of dynamic policy. We go from measurement to input. You have three images to design. And then in this case, the parameter will be AK, PK, CK, three images you want to design. And this represents the dynamic system here. And in this case, the dimension of the cassette is the same as the dimension of the state. So we say the full order policy. So, and for this problem, again, we can put the problem in this abstract form. You have a cost function, you have constraint, and in this constraint, we want to make sure this matrix to be stable. The eigenvalue of this matrix have negative real part. The ABC will be the parameter here. The problem data will be here. And this parameter in blue is some parameter you want to design for the policies. And then this will be the constraint. And for this constraint, we have example to show that it could be disconnected. It's not always path connected, but it has at most 2 path connected components. So we have example here connected, and another example this is path disconnected, but we only have 2 components. And this is always true. So for any constraint like this, you can at most have 2 path connect components. And again, I want to give you a quick proof for this result. The proof really goes for the same procedure as convection, but in this case, it's a little bit more complicated. The idea is that we can construct a convex set which based on linear matrix inequalities, similar to what we did before. And in this case, we also need to use another set, which is set of inverted matrices. And this is relevant to coordinate change of your dynamic policies. And based on this set, we can also construct a continuous surjective map to construct fully for this set. And now we know for this set of inverted matrices, it had 2 path connect components. One corresponds to positive determinant, and now corresponds to negative determinant. And here we have a continuous surjective map. So you will at most have 2 path connect components. And sometimes you only have 1 because these 2 components after mapping it intersect, and then you have 1. Otherwise, you have at most 2. Right? So again, the proof is based on convexification. So there's another representation for this set. Use some other variable which has convex properties. Right. And the second step is that now we need some quantification of the policy. So for a special class of policy which is controllable and observable, this again is a standard notion in control theory. If it is a station point, then it will be a global minimizer. Again, we have a local stationarity plus some information of the policy itself. This is just a structural information, controllable and observable. And then we have a global optimality certificate. So in this example, we can certify all the points on the right curve to be globally optimal using this statement. And you can also run gradient descent, and in some case, you will find this point in this definition. So even though the problem non-convex has path disconnected field region, we still have this useful statement. And this quantification is not redundant, because if the policy is not controllable or not observable, we can find suboptimal station point. For example, saddle point. So we have example we show you really a saddle point can appear in this LQG power optimization.
So what are the functions for their policy? Again, function is not true. So then unless your policy is very special.
Of course. Of course. So we have a very special setup, right? This is just the LQG problem. Then in this problem, we prove
talk about the physical set. Did not talk about the objective. So
yes. So
so in the set is the entire space, but objective is tricky. That actually you have everything.
So we prove 2 properties, right? So first for the physical region, and then for the cost function. We showed cost function is non-convex, but we have these good properties. And really the proof idea I'm going to show you in the second part is based on convex reformulations. It's not arbitrary non-convex function. It has some global structure behind it.
So is the integral of the quadratic function you mentioned, is that your policy? That's a very nice convex quadratic function.
No. Okay, so this is a misconception. Let's go back to this very simple problem, and you will see non-convex appears. Like this is a linear, this is a quadratic. Okay, fine. Both of them are convex in terms of U. But now you want to do feedback design. You want to say my input will be a function of your current measurement. This feedback loop will give you non-convex. So you want to design K. For K is a parameter. You want to design. You do not want to design an open loop input. You want to design feedback K. And now you see if you do this simple recursive expression, you see this is a non-linear dependency, and cos will be non-convex.
So what is your J here?
J just here. This summation. This is my J.
So this is a convex quadratic.
In terms of x and u. No, it's in terms of x and u.
So that is what we can discuss later.
Yeah. So this is like a misconception. Yeah. So yes.
So even if you show that it is connected, it is path connected,
Yeah.
the physical set, does that mean that gradient descent would go to?
No, it does not
It
mean.
doesn't mean.
It does not mean that.
Because it's not convex.
Right.
It's some,
Yeah, it still depends on-
gradient descent to make it.
Yeah, it still depends on your cost function. It depends on your cost function. So it means path connected just means potentially you can find a path. But then how to find path depends on your cost function. The cost function will guide you to find the path. And in LQR, because cost function is very nice, the cost function is gradient dominance. Set the gradient dominance problem. So cost function will guide you to find that path if you do gradient search. This is for LQR case.
I see. I mean, one thing might be very naive, but it seems like the Lyapunov, the P that you were finding to find the inverse mapping, right?
Right. Yeah.
So that should, like, if you change your gradient, your projection in some way to use that P, that might actually help you to find the
Yeah, that's a very good question. So right now, I didn't talk about any algorithm design yet. I just showed you there's some structural property for the problem. And then your question asked, how can we use this kind of existing convex information to guide my local search algorithm? This is a very interesting question. We do not have good result yet. But one difficulty people will argue is that this kind of convex information requires the knowledge of your model. And the one key advantage or one key argument people do possible is that you can ignore the model information. You just use your cost function, estimate a gradient, you can do. And this kind of reformulation requires the knowledge of A and B. This is your model information. So first, I think it's very good idea. Second, people may argue this may not be practical. You require the model information in this case. Right? Good. Okay, thank you.
People like part of three they estimate the gradient basically.
Yeah.
Using derivative premium.
Right. Yeah.
So I guess so it's not really like you're not really computing the gradients in practice. You're just doing like a derivative free algorithm.
Right. So that's basically these three papers. One key result is this fact. But they also talk about how to estimate the gradient from the cost function, how to control the variance. But those are standard results in zero order optimizations literature. Of course, they need to take care of the non-convex domain. So there are some starting points. Yeah, exactly. Yes, that's key feature. Yes, they not only show this set of gradient, they also show the function is L smooth over the sublevel set. And then L is a constant, you do super small step size, and then you can keep your iterate to be feasible. Yeah. Good. Great. Thank you for the questions. So all right, as we talk about, we see two proofs using convexification right now. And this second fact will be proved using convexification as well. I'm going to show you in the second part. So we talked about three cases in benchmark control, LQR, robust control, and LQG. And there are quite a few recent papers that identify favorable properties for non-convex parts of magnetic control. And here are some references. And there are also two survey papers which summarize the geometry and the theoretical analysis for parts of magnetic control. If you're interested, you can take a look at some reference here. All right, so we talk about some benign non-convexity, and you may be wondering there should be a reason. Like Professor Zheng Li mentioned, this property may not be universal. Of course, it may not be universal. You can find a very simple non-convex function. You will not have this property. So in the second part, I'll show you the reason I believe, also a very simple reason behind the benign non-convexity we mentioned earlier in the first part. So the idea is that if you look at policy organization, it is non-convex. Very easy to show. But at the same time, in the control literature, like almost 30 years ago, 40 years ago, people developed a lot of methods based on linear matrix inequality to solve control problem, like LQR, LQG, H infinity control. They have a linear matrix inequality based method, which will be a common reformulation. So our idea is just to say we are going to use LMI-based common reformulation for control problem to show the hidden convexity of policy optimization landscapes. And we are going to bridge this gap. We use this extended Convex Lifting to show the connection, and then we prove that for a class of non-degenerate policies, I'm going to define this next. We show all the Clark station points are globally optimal. Even the problem may be non-smooth and non-convex. And the reason really because you have a convexification in some sense. It's not obvious, but in some sense. So we can use the convex property, any local minimum global, to confirm in your origin space any station point will be global optimum. All right, so I think you can get this big picture. Let me give you a very simple idea to show what we are going to do. It's really simple. We have a two variable function, and if I want to minimize this function, and the function will be non-convex. If you do gradient search, probably will take some time to figure out a good step size and the strategy to solve this. But if you look at this problem directly, if you minimize this function, I think all of you take probably a few seconds, maybe at least 10 seconds, you realize the minimizer will be 1 and 0.5. The x2 should be 1, x1 should be 0.5. But very clear from the observation. So what you really did is that no matter whether you realize or you didn't realize, we are doing a changing variable. We say this is y2, this is y1. And formally you can put this in this form. Let us say we define a inverted map, y1, y2. And with this map, the function becomes so nice. It's just probably the simplest convex function. It's quadratic. And of course, this is a minimizer 1, 2. And this procedure is independent to whether the function is smooth or non-smooth. So you can do the same thing for these non-smooth functions. This all, again, you define this map, and you get a convex function. Here you have non-smooth case. But this doesn't matter because you have convex function, any local minimum will be global optimum. Right, so this is a very simple example, and we can generate this idea to control problem. Now we have a function in terms of two parameter k1, k2, your policy parameter. We have this function. Now this is a very explicit form of function. And from this expression, it may not be easy to see whether the function is convex or not. At least I cannot do this. It's very hard for me to see whether the function is convex or not. And this function really comes from a LQR problem. If you use this problem data, you can compute this function explicitly. Yeah. And from control theory, we can actually build a map explicitly. This from control theory, we can build this map. And with this map, if you use a new coordinate into the y, user function will be in this form. And now, probably take maybe a few minutes, you realize the function is convex. Because this function is a linear plus quadratic over some linear function. So maybe take 1 minute, but it's very easy to show this function is convex. And we plot it in the coordinate y1, y2. It's really a convex function. Okay. So with this observation, you may say, okay, let's formalize this observation. So let's consider a continuous time function here. And then we look at epigraph, the graph above the function. And we say, suppose there is a smooth and inverted map between your epigraph and a convex set. And this convex set should have some epigraph property. So we assume the map direct output the function value as the second argument. So really what you say is that you have non-convex thing, after method, you get a convex thing. And now you say, of course, if I minimize the non-convex function, this will be equivalent to minimize this convex function, because this map is smooth and invertible. And also you can show that any station point of the origin function will be global optimal. Again, this is because of this smooth and invertible map. Fine. And this is just a very simple form of the observation we did earlier. But now, is this enough for control problem? Yes. So we control the.
You might get in the combination that will be alpha.
Yeah, so here we did talk about local geometry, we just talk about the point. You want to control like how the local behavior geometry look like, you need to control the Jacobian of this map. Like I think we are talking about Jacobian inverse, right? But now we do not talk about the Green dominance of that property, we just talk about the one point. So at that point, you don't need to control the Jacobian. But if you want to control the local geometry, yes, you need to control the Jacobian to move some property from here to here.
Okay, it is control policy.
In this case, just a single k to be any prime you want to minimize, and in control this will be a positive prime in control. But here, just a general continuous continuous function. The k will be the feedback gain u equal to kx. Right. In LQR, we are going to restrict this to be the positive parameter in the linear feedback gain, and in LQG this will be dynamic controller. And in some other form, you could have some other parameters. So here I'm just saying this could be any functions, but you have a very strong assumption here. You have this smooth invertible map, which connects from non-convex to convex case. And actually this observation very simple, but actually is useful to show LQR. LQR problem can be proved by this fact, but for LQG cannot. For robust control cannot. So for LQR, you already can prove that good property using this fact, because we can really build a smooth inverted map for LQR problem. So for general control, we need to go a little bit beyond this idea to do a little bit further extension. Our idea is that, again, look at the epoch graph, but we need to introduce some extra variable. We need to do a lifting. From the epoch graph, we go to a high dimension space. We need to do a little bit lifting to high dimension space. And for this lifting set, we assume there exists a smooth invertible mapping, which connects this lifting set with a convex set and another set. Okay. So compared to the previous page, we have a lifting procedure here. So we have a lifting procedure, and then we also have another set, like auxiliary. This set will not matter in our guarantee, but we need to have this set to model control problems. Okay. So you may ask, why would you do lifting? Right? Why would you do lifting? Because in control, if you look at any control problem, very often you realize the upper function will be very useful. So normally a direct convexation is not possible in control problem. Normally you need to have a Lyapunov variable to help with your convexation problem. So the lifting procedure will correspond to Lyapunov variables in control. And then why we need another auxiliary set in addition to the convex set? This is because in this case, it will allow you to isolate some redundancy and symmetry in the original non-convex problem. So in this problem, you may have some symmetry going on. You may have some redundancy in policy parameters. And this set will help you isolate those kind of symmetry. And you only concentrate on the convex property in the reformulation. And in control, this is related to the coordinate change of your dynamic controllers. And this is really necessary when we try to analyze output feedback control systems. So this is not redundant when we try to analyze output feedback control problem, for example, LQG. So formally, we have this lift variable, and then we have this connection between a convex set, this is a convex set, and some other variables. And now with this picture, we can give you a formal definition of extended convex lifting. We say ECL. So again, we consider a continuous time function from an open domain to a real value. And now we look at two epigraphs. The first one is strict epigraph. So this gamma is strictly larger than your function value. And the second is the usual epigraph. This is bigger than or equal to the function value. So, and then we say a tuple is a extended convex lifting of your function if we have the following conditions. Actually, we have two conditions. The first condition is that the lifting set should be good enough to cover the strict epigraph, and the lifting set. Okay, this is after projection to your original variable and the function value. After projection, this should be good enough to cover the strict epigraph and should be small enough to be contained by the closure of your epigraph. So this set will really characterize the behavior of the function. And the second requirement is that we do need to have a diffeomorphism, which is just a smooth and invertible map that connect this lifted set and a convex set and with some auxiliary variables. And we direct output the function value to the map. Because we want to analyze function value, so this value should not be changed. So this output here. So we have this definition. So basically we have a lifted set, we have a convex set, and some auxiliary set, and a smooth mapping. Satisfy these two conditions. Right. And you may wondering, this look very special. This set, this inclusion look very special. So I want to say a few more things about this inclusion. Why we need this inclusion? And your first intuition could be why we cannot use this one directly. We just say the projection of lifted set equal to the epigraph. So will this work? Of course, this is a special case for this situation here. And this case is less restrictive. And this case works for more general situations. And if you use this condition, you can prove this is okay for state feedback control problems. This is okay. But this will be too restrictive for dynamic output feedback control. Because you cannot find a common reformulation satisfy this. So you may only be able to find a common reformulation satisfy this one. So, and this is a bit subtle in control systems. And now with this definition, you can see this inclusion. By definition, some point in the epigraph may not be covered in the lifted set, because this is just a part of the epigraph. And this includes the strict epigraph. So we say this point to be degenerate for this particular convex lifting. And for those kind of points, you may see suboptimal behavior. For example, saddle point. In the LQG, we really see saddle point coming from the degenerate point. And we say the variable k to be non-degenerate if this pair is covered by your lifted set. And now this will be well behaved. And actually we are going to show you for this kind of point, the staging point will be global optimum. So now we have two guarantees. First, if you have this convex lifting, we can prove that this is not difficult to prove. We can prove the minimization of the original problem will be the same as minimization for convex optimization for this convex problem. And the second guarantee is that for the non-degenerate point, because this point will be covered by your convex reformulation, any station point will be global optimum. And this statement really covers all the observation we talked about in the first part. Really, we can build a convex lifting for those kind of control problems.
The G set, the abilities, that's not.
Yeah, because that's good observation. So this set is here to help us build this lifting. Now this set, look here, this set does not depend on you. So this variable will not affect your gamma. And gamma is the function value you want to analyze. So it's just auxiliary, so it doesn't matter.
But you constrain about the GA between the reformulation. Why doesn't you constrain on the true? Why don't you constrain on
Yeah, so because you want to do minimization, you just minimize gamma over the first element. So this will be two set, and the gamma will be.
I see, because it's a product.
Yeah, it's a product. Yeah.
I see. Okay, so it doesn't matter in the product.
Yeah, you can drop that term. Yes, exactly. So it doesn't matter. So we have this term just because in some situation you need to have this term to build the convex lifting.
I see, but it doesn't affect strength.
Right. If you do minimize, you can ignore it. You can ignore it. And this also does not affect the station point characterization, because the function value only here. So this will be convex properties. Yeah. All right. So we have these two guarantees. Yeah. So I put it here because the proof the proof is really we try to find a direction derivative. So it's saying that if you at a station point, if it's not global optimal, we have another point which has a low cost value, and from these 2 points, after this map 5 in the convex set, we can build a continuous path, and that will give you a direction derivative which will be negative. And then we need to make sure the direct derivative and the Clark general derivative are the same to confirm it's not possible. It's a technical condition. Yeah.
It doesn't really matter because they have a diffeomorphism such the. I don't think you need, but okay, it's a technical thing.
Yeah, but this is already very general, so it is covered for all the control problem. And in our current proof, we leave this maybe for some further argument, but we are not entirely sure. So this is already sufficient for our case. Yeah, and this is already very general enough for parts of any control. All right, so I have another probably 5 minutes. I can give you how we build the Convex lifting for control problem. So really, because for all the control problem, there's a Convex lifting procedure, and you can make a statement about global optimality of station point. So again, this is an LQR problem. You have a linear dynamic, pay the problem you want to design. You have constraint, you have the cost, and this is the geometry you may observe in the landscape of parts optimization. And then we are going to build this procedure from the alpha graph. We build a lift set and we build a diffeomorphism, and then directly we prove the guarantee of station point being global optimal. So first, lifting. Lifting is really come from the upper variable. So it's very similar to the constraint case. You have the upper variable x into this, and then you have a convexification. You just change the variable. Just say kx equal to y. Just kx equal to y. So now the bilinear matching inequality become linear matching inequality. And then you just change the variable. Just say kx equal to here equal to y. And obviously this is a smooth and invertible map. And in this case, we do not need to use auxiliary set, and we can prove the projection of this set equal to that graph. So all the policies are non-degenerate. And then of course this theorem directly comes from our general guarantee. So this really comes from the Lyapunov theory, and we have a lifting procedure, we have a convex reformulation, and then directly we get this. And now look at the robust control, and the Convex lifting become different, but again standard in control theory. So we have this bounded real number property, and you see here you have a P and K couple, again bilinear, and you can do similar change of variable. You get a linear matching inequality, and this is just a similar change of variable. And this again is smooth and invertible. And in this case, we do not need to use a auxiliary set, and we can also prove the projection of each set equal to that graph. So all parts are non-degenerate. And then we can show this. Of course, we already show this H infinity or robust control cost function is subdifferential regular. That is another factor we to prove, but not very difficult. And then we directly use this claim. And for LQG, it's complicated. For the convex reformulation, it's very complicated. But again, it existed. So in the 1997, this was one of the major breakthrough in control theory, which show you output feedback control can be done using linear matching inequality. So based on this result, we can show a convex lifting exists for LQG. And in this case, we really need to use the auxiliary set. And this set will be the set of inverted matrices. And we can show a policy to be non-degenerate for this condition. And then we say we can say any informative station point is global optimal. And we also prove controllable observed policy are informative. So naturally it will be global optimal if it's a station point. And we can build other similar convex lifting for other control problems. And we talk about those kind of instances in our paper. So with that, I'm ready to conclude. So first I give you two messages. First, we say process organization in control is generally non-convex and possibly non-smooth. but they are benign in linear control. And we introduced a general framework called extended Convex Lifting, which identifies those benign properties. And really, we can say from local information, with some information of the process itself, we can guarantee global optimality. And like I mentioned, we didn't talk about algorithm design in this talk. And actually, still there are some open questions: how we design efficient local city algorithms, how we prove conversion rate, or how we deal with this kind of degenerate policy, which could be a set point, or how can we extend the guarantee beyond the linear control. So overall, we would like to combine result in control theory, convex and non-convex optimization, and the reinforcement learning to design principal algorithms to achieve better performance for general control systems. So with that, I thank you for your attention, and these are some select references, and open for any question if you have. Thank you.